In this video tutorial, we will introduce the topic of chemical nomenclature. So one of the common questions I get when I teach nomenclature is why? Why are there so many different ways to name chemical compounds? Why can't we just have one naming system? What's the point of having all these different ways of naming chemical compounds? To answer this question, let's be racist. I have a friend. My friend's name is Liu Ming Wei. You've never met my friend before, but tell me, what do you think his natural hair color is? What do you think his natural eye color is? Do you think his parents wanted him to be a doctor? Okay, now you're being racist. But I think most of us would have been able to predict that his natural hair color is black and his natural eye color is brown. Even though you've never met him before, you're still able to make some predictions just based on his name. But not just his name, the type of name this is. And in this case, it's a Chinese name. Now, are you going to be 100% correct all the time? No, but at least it gave you a starting point. Well, it's the same thing. Just as different cultures have different naming systems, different types of chemicals also have different naming systems. And we use these naming systems in order to help us predict what kind of properties that compound is most likely to have. So for instance, barium sulfide. I've never used barium sulfide before. I've never seen it before. But because it uses a binary ionic naming system, it probably has the properties of an ionic compound. High melting point, high boiling point, electrical conductivity if dissolved in water, typically soluble in water, etc., etc. So how a chemical compound is named tells you a lot about its properties. Alright, now that you know why we have so many different naming systems, let's learn about them. The first naming system is for binary ionic compounds. So only use this naming system when there are two elements involved. Alright, so that's why the word binary is there. If you see more than two elements, don't use this naming system. It'd be inappropriate and confusing to the reader. Next up, it must be an ionic compound. So typically the first element should be a metal, the one with a positive valence charge, while the other one should be a non-metal. So it'll have a negative valence charge. Now, in a traditional marriage, one partner keeps their last name while the other partner changes their last name. Well, same thing. When sodium and chlorine chemically combine, when they get married, if you will, the second element, the non-metal, the one with a negative valence charge, changes its name. It went from chlorine to chloride, so there was a suffix change. Same thing down here. When barium and sulfur are bonded together, the non-metal, sulfur, changed its suffix to sulfide. So the general format for this naming system is element, elemenide, where the first element, the metal, the one with a positive valence charge, does not change its name, sodium, barium, neither of these change their names, while the second element, the non-metal with a negative valence charge, changes its suffix to IDE. Chlorine turned to chloride, sulfur turned to sulfide. Alright, so if you look at the periodic table, to the left of the staircase are the metals. These guys generally will not change their names. Barium didn't change its name. Sodium didn't change its name. But the non-metals on this side of the staircase did change their names. So we had the chlorine turn to chloride. The sulfur turned to sulfide. Now, some students have difficulties with the name change, but it's not as bad as you imagine it to be. Many of these names will come naturally to you. I mean, which sounds more correct to you? Oxygenide or oxide? Fluorinide or fluoride? Chlorinide or chloride? Alright, so most students already have a pretty good idea of what sounds right and what doesn't. But if you don't, these are the ones you need to worry about. For the most part, these are the only name changes you need to worry about for high school science. Now, just so you're aware, I like to spell sulfide with a PH. This is the British or the Canadian way of spelling sulfide. If you want to spell it with an F, that is the American way of spelling sulfide. Both are acceptable, so I won't deduct marks on the test, but I will deduct my respect for you if you use the American spelling. Alright, so let's try some examples. I find it's easier to go from the chemical compound to the chemical name first, and then we'll do the chemical name into the chemical formula afterwards. So, looking at this chemical symbol, Na, we see that it is sodium. And since sodium is on the left side of the staircase. It's a metal, and metals do not change their names, so we just keep it as sodium. Now sulfur is on the right side of the staircase, so it's a nonmetal, and the nonmetal must change its suffix to an IDE, giving us sulfide. You'll notice that I ignored the subscript 2, it's not in the name over here. I'll tell you when that is going to be necessary later. Let's try one last one here. So Zn is zinc. Zinc is on the left side of this staircase, so it's a metal. Metals don't change their names, so we're going to leave it as zinc. N is for nitrogen, and it's on the right-hand side of the staircase, so it's a non-metal. Non-metals will change their suffix to an IDE, so we end up with nitride. Again, I don't worry about the subscripts. That'll be for another time. So now that you're able to go from the chemical formula to the chemical name, we can go the other way around. Go from the chemical name to the chemical formula. Now this direction does require an extra step, but no big deal. First, we're going to write out the chemical symbols. Calcium is a Ca, while chlorine is a Cl. So Ca and Cl. Next, we need to identify the subscripts, the numbers at the bottom. In order to do that, we must first identify what are the valence charges of calcium and chlorine. Now, if you look at the back of the periodic table, you'll see that calcium has a valence charge of 2+. That's because calcium is in group 2 of the periodic table, so it has 2 valence electrons. And in order to achieve stability, it needs to lose these 2 electrons so it has that full outer valence shell. In so doing, it becomes a positive calcium cation with a charge of 2+ because it lost these 2 electrons. And that is where the 2+ valence charge comes from. So I'm just going to write its valence charge above the element symbol itself. Looking at chlorine, we can see that its valence charge is a 1-, and that's because chlorine is in group 17 of the periodic table. So it has 7 valence electrons. In order to achieve stability, it needs to gain 1 more electron so it can have that full outer valence shell, the octet structure that provides stability, and in the process become a negative chlorine anion with a charge of 1- because it gained an extra electron. And that explains why chlorine has a 1- valence charge. So the valence charge number essentially describes how the element is going to achieve stability, either by losing electrons with a positive charge or gaining electrons with a negative charge, while the number itself tells you how many electrons are involved in order for that element to achieve that full octet structure and gain stability. Now that we have those valence charges, we can use something called the zero-sum rule to determine what these subscript values are going to be. So the zero-sum rule states that an ionic compound is considered to be stable if the sum of its valence charges adds up to 0. So the valence charge for calcium is a 2+, while the valence charge for chlorine is a 1-. If I try to add up these valence charges, I get a 1+. That's not 0. I need to make sure that when I add these valence charges, it adds up to 0. So that means I don't have the right number of atoms for this compound to be stable. Well, what happens if I use 2 calciums instead? So I put the number 2 down here. Now that I have 2 of these calciums, I have 2 of these valence charges. Now, when we recalculate this, does that help? No, we end up with a 3+, it's not a 0, so that didn't work. So what if I tried having 2 chlorines? Well, with 2 chlorines, I will now have 2 valence charges of 1-. And when you add a 2+ with a 1- and another 1-, you end up with a 0. And that tells us that this chemical formula with these subscripts, these numbers down here, is correct. And that's what the zero-sum rule does. It helps us to keep track of how many electrons are being lost and how many electrons are being gained. So while calcium loses 2 electrons and each chlorine gains 1 electron, in order for this entire compound to be stable, I need 1 calcium but 2 chlorines. So for every electron that was lost, it's found a new home. And when this happens correctly, the valence charges add up to 0. Now, I know some teachers like to use something called the crisscross rule. That's where you take these charges and crisscross. So you put the 2 down here and you put a 1 down here. Now, if we don't put a number here, we always assume it's a 1. Now, I personally don't like the crisscross rule because there's no thinking involved. All right, you're just crisscrossing. Why are you crisscrossing? Why does it have 2 chlorines? Why is it 1 calcium? I don't know, I'm just crisscrossing. You're just blindly doing something that you don't understand. While the zero-sum rule forces you to think about how many electrons am I losing, how many electrons am I gaining, and if I can add them up to 0, that means each electron has found a new home. If the value is not 0, that means you've either got an extra electron or less electrons than you need to achieve stability. So the zero-sum rule forces you to think about the chemistry and the movement of electrons, while the crisscross rule is just you blindly crisscrossing. The second reason why I don't like the crisscross rule is because it won't work in some instances. There will be some situations where the crisscross rule will actually give you the wrong answer. So, if you never intend to take chemistry ever again and you have no clue what the heck is happening, then by all means crisscross to your heart's desire. But if you ever plan to take chemistry again, then you definitely need to understand the zero-sum rule and think about the movement of electrons, and not just blind memorization. Alright, so now that I know what the subscripts are, I can erase the valence charges at the top, just to clean things up because that was rough work, and my final answer is CaCl2, calcium chloride. Let's try one more example, calcium nitride. First step, write the symbols out. Calcium is a Ca. Nitride used to be called nitrogen, so that's an N, so we get a CaN. Now let's look up their valence charges. Calcium has a valence charge of 2+, while nitrogen has a valence charge of 3-. Now when we add up their valence charges, 2+ and a 3-, we end up with a 1-. That's not a 0, so that means these subscripts are not correct. Now here's a hint. Anytime you see the numbers 2 and 3 in chemistry, you should automatically be thinking of the number 6. That's because 6 is the lowest common multiple between 2 and 3. So how many of these calciums do I need to get 6? Well, I would need 3. 3 calciums, each one is worth 2. 1, 2, 3 calciums, giving me a total of 6 positives. I would need 2 nitrogens, each worth 3-, so 2 nitrogens, and that would give me a 6-. 6+ added to a 6- gives me a 0, and my zero-sum rule works. So this shows me that during this process I lost 6 electrons, but then I also gained 6 electrons. So for every electron that was lost, it found a new home. That's what the 0 represents. No one left behind. Alright, this is not like IKEA furniture where I'm allowed to have extra pieces behind. This has to be perfect. So my chemical formula is Ca3N2. Again, if you're desperate and you have no clue what to do, then by all means, crisscross. Bring the 2 down here, bring the 3 down here, you'll get the same answer. It won't work in every situation, but if you're never going to take chemistry again, who cares? Now that I have my subscripts, I can delete my rough work at the top. And the chemical formula for calcium nitride is Ca3N2. I need 3 calciums and 2 nitrogens to achieve stability for the entire compound. The next naming system we're looking at is called polyatomic ions. The prefix poly means many, and atomic, well, atoms, so many atoms. So use this naming system when you see more than 2 elements involved. So over here, sodium phosphate, I see sodium, phosphorus, and oxygen. So there's 3 atoms involved. Sodium hydroxide, Na, O, and H, 3 elements involved. Now, polyatomic ions are a special grouping of atoms. These groupings of atoms are extremely stable together, and during a chemical reaction, they rarely break apart. They typically react as a group. So because they react as a group, we gave them their own names. Bromate, a bromine and 3 oxygens stuck together with a 1- charge. Iodate, an iodine and 3 oxygens stuck together with a 1- charge, etc., etc. Now the hard part is recognizing the difference between a bromate and a bromide. With the IDE suffix change, we're just looking at a single element of bromine. But when you see the ATE suffix, that's telling you that it's a compound ion. Now, I like to put brackets around it to remind myself that bromine, attached to 3 oxygens, this grouping of atoms, has a 1- valence charge overall. So this 1- charge belongs to the entire group of atoms, while this 1- charge belongs just to the bromine itself. Now, most polyatomic ions will have an ATE suffix, however some of them do not, like ammonium for instance. A single nitrogen bonded to 4 hydrogens with a 1+ charge, or hydroxide, an oxygen bonded to a hydrogen with a 1- charge. So there are a few exceptions here and there, but for the most part they do end up with an ATE suffix change. So, in general their format follows element, compound ion name. Remember that the positive ion, the metal, generally will not change its name. So sodium didn't change its name, first element. Hydrogen didn't change its name, first element. But the second one is the compound ion name, the phosphate, the hydroxide, the permanganate. All right, so let's try an example. Ca is a calcium, while the IO3 is not iodine, because that's just one iodine, but rather IO3 is iodate. So calcium, iodate. I think you can do the rest of these yourself. Let's go over to the other side where we're trying to find out the chemical formula from the chemical name. So let's first write out their symbols. Calcium, Ca, while phosphate is a PO4. Now I'm going to put a bracket around the PO4 to remind myself that it's a package. It's a grouping of atoms, and it has its own unique valence charge. So a 3- for the phosphate and a 2+ for the calcium. Now, in order to zero sum, as I mentioned before, whenever you see a 2 and a 3, the number I think of is 6. And in order to get the 6, I need to have 3 calciums, each one worth a 2+, so 3 calciums, adding up to 6+, and 2 of these phosphates, each one worth a 3-, so 2 of them, and that adds up to 6-. Add them up together and we get a 0, so every electron that was lost has been gained by another atom, so they've all been accounted for. Now, it's very important that you keep the brackets on for this situation because we're telling the reader that we have 2 of these phosphate groups. So 2 of these 3- charges. Otherwise, if you remove these brackets, someone might read this as 42 oxygens, and that's messed up. There's no way you're going to cram 42 oxygens around this one small little phosphorus. So make sure you keep that bracket on. All right, we've got the subscripts. Let's erase the rough work at the top. And you've got Ca3, PO4, calcium phosphate. Let's do one last one, potassium chlorate. Potassium is a K with a 1+ charge, while nitrate is an NO3, so nitrogen with 3 oxygens combined with a 1- charge. When we try to add up the valence charges, 1+ and 1-, we get a 0 without having to do anything. So only 1 potassium and 1 nitrate ion is required to achieve a stable structure. Since the number 1 doesn't have to be written in as a subscript, we can leave it as such. Now in this case, you don't need the brackets around the polyatomic ion because keeping them or removing them doesn't really change a thing. But if you're not sure whether you should keep the bracket on or keep it off, my recommendation is just to keep it on. It's not good form and people will probably laugh at you, but you're technically not wrong. It's like using brackets over here, 1 + 2 + 3 = 6. Do you really need these brackets? No. Is it technically wrong? No. But you are going to look silly doing this. So I'm going to get rid of the rough work. And actually there's too much of a gap here. So I'm just going to bring it in a little closer. And so my final formula is potassium, nitrate, KNO3. Now the next naming system is called binary molecular or sometimes binary covalent. Again, only use this naming system when there's 2 elements involved. That's why it says binary. And only when it's a molecular or covalent compound. So that would be when the 2 elements are nonmetals on this side of the staircase. Now because we're only dealing with nonmetals, and nonmetals typically have a negative valence charge, it won't be possible to follow the zero-sum rule because both sides would be negative and you'd never add up to 0. So in this case, we need to use Greek prefixes, di and pent for instance, to denote how many of each element is present in this particular compound. So these are the Greek prefixes that you're responsible for. Most of them should make sense, like mono is 1, octa is 8, deca, decade, 10, pentagon, hexagon, 5-sided, 6-sided, triangle, 3-sided. Really the only ones that give students trouble are di. Sometimes they'll say bi, but it's actually di, so like carbon dioxide, and that's 2. I have students say quad sometimes, but it's actually tetra for 4. This one gives a lot of students issues because a lot of French students think it's septa, but it's not French, this is Greek, so it's hepta for 7. So if I say dinitrogen pentoxide, I know that there are 2 nitrogens, dinitrogen, and there are 5 oxygens, O5. Alright, so dinitrogen pentoxide, N2O5. Now there are some grammatical rules we'll have to follow. So the first rule is the prefix mono should only be used on the second element. All right, so carbon dioxide, carbon dioxide. You don't call it monocarbon dioxide, so the mono is not necessary for the first element, but it is necessary for the second element. So in this example, I would say carbon monoxide, because there's one each. You don't say monocarbon monoxide. And that brings us to our second rule. If two vowels are adjacent, so that if the two vowels are side by side next to each other, remove the vowel from the prefix itself. So in this case over here, I don't say carbon monoxide, so because there's mono over here, the O from the mono and the O from the oxide are side by side. Don't call it monoxide. You must instead delete the vowel, delete the vowel from the prefix and leave it as such, carbon monoxide. But the letter I is an exception. All right, so take a look at this one, carbon dioxide. You can't just go, oh, I, O, two vowels next to each other, therefore it's carbon dioxide. No, that's wrong. You must keep the I there. Carbon dioxide. So once you get over these rules, this naming system is pretty straightforward, pretty easy to do, sometimes too easy to do. So for instance, a common mistake I'll see students make is over here, Na3PO4. I've seen some students write out trisodium because there's 3 sodiums, monophosphorus because there's only 1 phosphorus, tetraoxide. Now they made a mistake here because there's 2 vowels side by side, so you have to remove the A from the prefix and just say tetroxide. So trisodium, monophosphorus, tetroxide. Ooh, sounds scientific, but wrong. Remember, this naming system is called binary molecular. You've got more than 2 elements here, 1, 2, 3, sodium, phosphorus, oxygen. You have 3 elements here. So it's definitely not binary. And both elements, because they're molecular compounds, should be nonmetals. They should only appear on this side of the staircase. Now you're fine with the phosphorus and the oxygen. Those are definitely nonmetals. But sodium is a metal. So remember, this naming system can only be used if both elements are nonmetals, so they appear on this side of the periodic table. If you see any elements that appear on this side of the periodic table, you're not allowed to use this naming system. Alright, so let's do one example. How about this one? N2O. N is the nitrogen, but it says 2 of them, so I need to write in di-nitrogen. And finally, there's 1 oxygen, so I'll call it an oxide. But there's only 1 oxygen, so I must write down monoxide, where I remove the 1 oxygen from the mono because there'd be 2 vowels side by side. So the final naming system we'll be looking at is the one that involves multivalent charges. As I mentioned earlier, these valence charges tell us how many electrons must be lost or gained for that atom to achieve stability, to achieve that full octet structure. While many elements only have one way to achieve stability, some have multiple ways to achieve stability. So antimony, for instance, and arsenic can either lose 3 electrons or lose 5 electrons to achieve stability. We say that these elements that can do that are multivalent. They have multiple valencies. Whereas boron and bromine typically can only lose 3 or gain 1 because they only have one option. We say they're monovalent. They only have 1 valence charge. Again, be aware, technically every element is multivalent, but these are just the most common valencies you will encounter. So although bromine may have other options to achieve stability, those are very, very rare situations. These are the most common ones you will encounter in our course. So let's look at this example, iron 3 oxide. First, I'm going to write out the chemical symbols. Iron is Fe, and oxide or oxygen is an O. In order to determine the subscript values, what numbers go at the bottom, we need to identify what are their valence charges. Oxygen has a valence charge of 2-, while iron is multivalent with 2 options, 2+ or 3+. But which one should we use? Should we use iron 2+ or iron 3+ when we're doing the zero-sum rule? Well, that's where this 3, this Roman numeral, comes into play. It says it's iron 3, so this tells us which species, which version of iron 2 or iron 3, am I looking at. In this case, it says iron 3 oxide, so I know it's not iron 2, but it's iron 3. Now that I know which version, which species of iron we're looking at, I can start doing my zero-sum rule. As I saw before, 3 and a 2, I automatically think of the number 6, which means I need to have 2 of the iron 3 pluses, giving me a 6 positive to work with, and 3 of these oxygens, giving me 6 negative charges altogether. Add them up, we get a 0, so for every electron that was lost, it's found a new home, and 2 irons to 3 oxygens is the right ratio to make this stable. So the chemical formula for iron 3 oxide is Fe2O3. Now if this had been an iron 2 oxide instead, then I know that it couldn't be a 3 plus charge. It must have a 2 plus charge. 2 plus and a 2 minus adds up to 0, so I don't have to worry about putting in subscripts here. But as you can see, it is very important that you include the Roman numerals to tell me which species of iron we're looking at. If I just gave you the word iron oxide, you wouldn't know which version I'm talking about, because iron 2 oxide will kill you, but iron 3 oxide will kill you faster. So they do have different properties. Now for this naming system, you do need to know your Roman numerals. So 1 stick is a 1, 2 sticks 2, 3 sticks are 3, but a V represents 5. So 1 stick before the V is a 4, 1 stick after the V is a 6. Now, you really only need to know up to 5 for this course. Past 5 I'm not super concerned about, but just make sure you know the first 5. So let's do a sample question. Mercury 2 sulfide. Mercury's symbol is Hg, and it is multivalent with 2 options, 1 plus or 2 plus. While sulfide, used to be called sulfur, is monovalent with a 2 minus charge. Since it says mercury 2, I know that it's the species of mercury, not mercury 1. So I can cross that one out. Now that I have a 2 plus and a 2 minus, they add up to 0. So everything is 0 summed. I don't need to put any subscripts here. I'm going to erase my rough work at the top. And the chemical formula for mercury 2 sulfide is HgS. Now going in the opposite direction is always a little more difficult. But let's try it out. Pb is lead. And lead has a valence charge of 2 plus and 4 plus, so it's multivalent, while sulfur has a valence charge of 2 minus. Now, unfortunately, this chemical formula doesn't tell me which version of lead it is, which species. Is it lead 2 or is it lead 4? So I do need to do some detective work. I know I have 2 of these sulfurs because the chemical formula says S2, so there's 2 of them, and each sulfur is worth a 2 minus, so I'm going to put 2 of these 2 minuses together. I only have 1 lead because the formula shows that there's no number here, so I only have 1 lead. Now which of these 2 numbers, when I put it in here, would add up to 0? If I put in lead 2 plus, does this equation work? No. 2 positives with 2 of these 2 negatives adds up to 2 minus, and that's not right. So I can cancel out this 2 plus, and it must be the 4 plus version of lead. So with the 4 plus added to 2 of these 2 minuses, now we zero sum. So every electron, all 4 electrons that were lost by the lead, were gained by these 2 sulfurs. So now we can call it lead 4 sulfide. And there's no need for you to tell me it's sulfide 2. All right, that's not necessary because there are no other options for sulfur. So that's not necessary in this case. So we'll take that out. Now, what if you didn't learn about the zero-sum rule? What if you only did crisscrossing? This is where students make their mistake, because if they crisscross, they take the 2, they punch it up. Oh, it must be lead 2, not lead 4, and that would be wrong. And that's why I don't recommend the crisscross rule, because you aren't understanding why you're doing things, you're just crisscrossing. And if you crisscross in this case, on a test, I would also crisscross because you're wrong. Alright, so PbS2 is lead 4 sulfide. Now another common mistake I see students making is iron 3 chloride. Here's how they'll do it. They'll say iron 3 and write down iron 3. But that's wrong. This 3 and this 3 are 2 different numbers. This 3 refers to how many irons there are when we're doing the zero-sum rule, while this 3 refers to which species of iron we're talking about. Is it iron 2 or iron 3? So since we're talking about iron 3, I know we're not talking about iron 2. And in order to zero-sum this, I would only need 1 iron, but 3 chlorines. So not 3 irons, just 1, worth a 3 plus. But I do need 3 of these chlorines, each one worth a 1 minus. So iron 3 chloride should be FeCl3 and not Fe3Cl. Alright, so when I say iron 3, I don't mean iron 3, I mean iron 3. Alright, so in grade 10 you probably didn't have to learn this method, but grade 11s you do now. This is just a fancier way, a more confusing way, to tell us which species of iron are we talking about. Is it iron 2 or iron 3, copper 1 or copper 2? So it's used for multivalence. Now we're not supposed to use this method anymore. Unfortunately, a lot of people still do. So a lot of chemical manufacturers, your professors in university or college, they'll still probably use this old naming system. I mean, everyone is supposed to be using the metric system. Kilograms, meters, liters. Sadly, we have the American and the British who are still using the imperial system. Pounds, inches, feet. So because this method is still active, I need to teach it to you so you are aware of what is out there. So this method requires us to know the Latin names for various elements and also their suffix change from "ic" to "us." In general, we only use this naming system for elements with classical names. We're not supposed to use it for elements with English names. So for instance, O matches with the English name, no problem, oxygen. So does nitrogen, N, carbon, C. But if you look at copper, Cu, iron, Fe, tin, Sn, these are using their Latin names. So technically this naming system is supposed to be meant for these guys over here with Latin symbols. So these are the only elements I need you to know the Latin names for. Iron was ferrum, now it's ferrous if it's a lower valence, or ferric if it's a higher valence. So notice the suffix change. If you have IC for a suffix, choose the higher number. If you have OUS for the suffix, choose a lower value. Cuprous, 1. Cupric, 2. Plumbus, 2. Plumbic, 4. So this other naming system we learned up here is much better because it actually tells you what the number is. Iron 3, iron 2. But this method requires you to have those charges memorized. So instead of saying iron 3, you would say ferric oxide because 3 is higher than 2. While iron 2 would be called ferrous oxide because the OUS suffix is for the lower number. Now, as I mentioned before, you're supposed to only use this naming system for Latin names. Unfortunately, you will see some people mixing it up with English names as well. So for instance, mercury, its symbol is Hg because the Latin name was hydroargyrum, which means liquid silver. So the symbol for silver is Ag, argyrum, while hydro means liquid or water, so silver water. So technically, we should be calling it hydroargyrus if we're going to use this naming system, or hydroargyric. But because this is hard to pronounce, a lot of people just use the English name, mercurus and mercuric. So that's why I'm not crazy about this naming system. It's pretty wishy-washy. But if you go into the back room where I keep all the chemicals at school, you'll see a lot of substances are still labeled using this method. Let's try an example. Stannic sulfide. Stannic is tin with a symbol of Sn, and because there's IC, it's the higher valence, not 2, but 4. And now when I look at sulfide, sulfur is typically monovalent with a 2 minus. And in order to zero sum this, I need 2 sulfurs in order to add up to 0. So Sn, S2. Stannic sulfide. Now just be aware I purposely put in some English name ones, like nickel for instance. Nickel symbol is Ni, that matches up with its English name, so I'm not supposed to use this. But just in case you ever encounter it, I hope not, you at least know what nickelic and nickelus means. That sounds stupid. But in any case, nickel has a 2 and a 3 for the valence charges. So the ic suffix gets the higher valence, 3+, while the OUS suffix gets the lower one, 2+. If I look at phosphorus, I see that it has a 3- charge. And I need to find out which of these two species would allow this to zero sum, since I only have 1 nickel and 1 phosphorus. So in this case, it must be nickelic, not nickelus, because it has to be nickel 3 in order for this to zero sum. So get rid of this one over here, and we'll call it nickelic phosphide. Again, this is stupid. You would never see this. I hope you would never see this, but I'm putting it in just in case you ever do. Alright, so the last topic we need to talk about are polyatomic family variations. This typically applies to polyatomic ions that have multiple oxygens inside their chemical formula. By changing the prefix and the suffix, we can tell the reader how many oxygens are actually inside the polyatomic ion. So let's take a look at chlorate for instance, ClO3 with a 1- charge. So I'll just write that as chlorate, and that's unchanged from the polyatomic that you're used to. But if I add a per as a prefix, so now it says perchlorate, that means I have 1 extra oxygen than I normally would have from chlorate. So now it's a ClO4 instead of a ClO3. Now the valence charge doesn't change because it's still part of the same family, but now you have a ClO4 for perchlorate. Now if you change this suffix to an ite, ite, you would get chlorite. And an ITE suffix means you have one less oxygen than you would with the ATE. So now I have ClO2 instead of ClO3. Again, same valence charge, same family. Finally, if I add the prefix hypo, so hypochlorite, that means you have two less oxygens than the regular one you have up here, chlorate. So now you have ClO with a 1- charge. Alright, let's try this one out. Sodium persulfate. I know the regular sulfate is an SO4 with a 2- charge. SO4 with a 2- charge. But by adding the prefix per in front, now that tells me I have one extra oxygen than I normally would have. So instead of SO4, it's SO5, again with a 2- charge, so the valence charge doesn't change because it's still part of the same family. So if I were to write out this chemical formula, sodium is an Na with a 1+ charge, while persulfate is an SO5 with a 2- charge. From here, just zero sum, so I'll need 2 of these sodiums, and now I've got a stable compound, sodium persulfate, Na2SO5. Let's try one last one. Nah, bro. So the BRO reminds me of bromate, BRO3, with a 1- charge. But since it's BRO, I know that it's lost 2 oxygens since then. So not BRO2, but BRO with a 1- charge. So this must be a hypobromite. Alright, so sodium hypobromite. Alright, in our next video tutorial, we will discuss balancing equations and the different types of chemical reactions.